So we have a worksheet right here, and it says, question 1, use a truth table to show that the biconditional statement P and Q is logically equivalent to P and Q or not P and not Q. So we're going to use a truth table to justify the result of this. So let's construct our truth table. Then it says, hence, use algebra of proportion to show that the negation of this statement is equivalent to this statement. So we're going to do part A first, using the truth table. So this should be about fine. So let me see, we're going to have P, then we're going to have Q, then we're going to have the biconditional statement, P if Q and Q if P. Then we're going to need P and the Q. Then we're going to need the negation of P. Then we're going to need the negation of Q. Then we're going to need the negation of P and the negation of Q. Then we're going to need, finally, then we're going to need P and Q or the negation of P and the negation of Q. So that's all that we're going to need. So let's go ahead and do this question. Let's finish draw this table. Alright, so let's finish drawing up the table. One line right here, one right here, one right here, one right here. Then we have not P, then we have not Q. Boom, boom. So we're done now. We're nice. So right here, so now we have P and we have Q. And so we want P. P is going to be true, true, then false, false. Then the next thing we need is Q. Q is going to be true, false, true, false. Then what we need is the biconditional statement P implies Q. And so the biconditional statement of P implies Q, what that is going to be is this biconditional statement. Remember, when both of them are true, it is true. When both of them is false, then it is also true. And so right here is true, and right here so is true. Then the next two is false. Then we need P and Q. P and Q is true only when both P is true and Q is true. So right here is true for P and Q is true. Everywhere else is false. Now the next thing we need is not P. Not P is going to be false, false, true, true. That's not P. And so then we need not Q. Not Q is false, true, false, true. Now the next thing that we're going to need is not P and not Q. Now not P and not Q, we're looking for when both not P and not Q is true. Not P and not Q is true right here, then everywhere else is false. So now we need P and Q, or not P and not Q. So P and Q, P and Q, P and Q is right here. So we're looking at this column, P and Q, or not P and not Q. So looking at these two. So true or true is true, and false or false is false. And so false or false is false, then false or true is true. So now what we can conclude now is clearly the biconditional statement, its truth result is the same as this right here. And so hence, so you can just write now hence, always write a conclusion. Hence, you can write that the biconditional statement of P if and only if Q, it is logically equivalent to P and Q, or not P and not Q. So we've just shown it now. Alright? So we just show it. So the biconditional statement is logically equivalent to that statement. Right? Given that their truth results are the same. Now it says hence. It says hence, use algebra of proportion to show this. Hence, meaning we're going to use this result to prove this. So let's do that. Alright? So we've just deduced that P, the biconditional statement, is logically equivalent to P and Q, or not P and not Q. We've just deduced that, right? So now we're going to prove the negation statement now. So let's start with the proof now. This is the proof. So now the left-hand side that we have, LHS means left-hand side. It's logically equivalent to the negation of P if and only if Q. Now the negation of P if and only if Q, that's logically equivalent to the negation of, now we just said that P if and only if Q is this statement right here. So it's the negation of P and Q. So I'm making a substitution for this statement right here. And it's the same as P and Q, or the negation of P and the negation of Q. So that's what we have. Now, if we expand in here, we're going to expand in the negation. What we're going to then get is, it is equivalent to the negation of P and Q, and then the negation of or becomes and. We just learned this, the negation of or is and. Then we're going to get and the negation of P and the negation of Q. And so what we're getting now is then that the negation of this part becomes the negation of P, and then the negation of the and becomes or, then we have the negation of Q. So that's what this side works out to be. Then write and the negation of the negation. Now we just learned that the negation of the negation, the complement law, states that this becomes P. Then the negation of and is or. Then the negation of the negation of Q is just Q. Now, of course, we can always change the order. A and B is the same as B and A. So we can change the order and write this as P or Q, P or Q, and we can write it as not P or not Q. and that is our right hand side. This was our right hand side, and so we've just done the proof using law of algebra proportion. Soft, very easy question. Alright, and that's how we use law of algebra proportion to prove that two statements are logically equivalent. It's easier to use the truth table, but likewise we can use algebra to do the question. Easy. Now let's look at question 2. Question 2 says construct a truth table for P implies Q and not P or Q and P and Q, not Q, and then determine the logical equivalence between the following. So let's construct a truth table and determine the relationship between each of these. So let's construct a truth table. So first we draw up our box right here. And so of course we're going to need P, then we're going to need Q, then we're going to have P implies Q, then we're going to need not P, then we're going to need not P or Q, then we're going to need not Q, then we're going to need P and not Q. So this is fine. So this is all that we're required to construct. So let's go ahead and do this now. So we have P, and P is true, true, false, false. Then Q is going to be true, false, true, false. True, false, true, false. And then what we need is P implies Q. So P implies Q right here. P implies Q is going to be, P implies Q right here is going to be true, false, true, then true. And how do we know that? The only time a conditional statement is false is when the antecedent is true but the consequent is false. That's the only time it is false. True, false, then true, true. Then right here now, we have the negation of P. The negation of P is going to be false, false, true, true, because we're negating P. Then the next table that we need is not P or Q. Not P or Q. And not P or Q is we're looking at not P or Q. These are the two that we're looking at. So true or false is clearly true. False or false is false. True or true is true. And then false or true is true. Alright. And right here now we need is not Q. And not Q is going to be false, true, false, true. So we have false, true, then false, true. Then the next thing we need right here now is P and not Q. P and not Q. And so P and not Q, we're looking at P and not Q right here. And so true and false is false. True and true is true. Then false and false is false. Then false and true is false. So now let's determine what we have. Now let's look at the truth table for P implies Q and the truth table for not P or Q. So looking at the two of them, P implies Q and not P or Q, the truth table are the same. And so determine the logical relationship between them, we can conclude that P implies Q is logically equivalent to not P or Q. They are logically equivalent because they have the same true result. So that's the first one. Easy, soft. Now let's look at the relationship between P implies Q and P and not Q. So this is P implies Q, and we're looking at the relationship between P and the not Q. So the relationship between P and the not Q, notice that when we have true here, we have false here, so. When we have false here, so we have true here, so. And when we have true here, so we have false here, so. When we have true here, so we have false here, so. And so both of them are the negation of each other. So how we can write it? We can write that P implies Q is logically equivalent to the negation of P and not Q. That's one way of writing the relationship. Or I'm going to put comma for another way you could write it. You could write that, some people might go ahead and write that the negation of P implies Q is logically equivalent to P and not Q. Either one of those is right, the answer is correct. Then the third and final one, it says what's the relationship between not P or Q and P and not Q. So it's relationship between this and this. Clearly these two are just, again, negation of each other. And so the negation of P or Q, that's logically equivalent to the negation of, in bracket, P and not Q. So those are the relationship. Those are the relationship between the two. Alright? So that's it, easy stuff. And that takes care of question 2. Then now the final part says use algebra of proportion to show that P and P implies Q is logically equivalent to P and Q. So let's do the third part right here. Alright, so we're going to do the third part right here. Our second part, however we want to put it. So I'm going to use the color dark blue. Alright, so our left hand side is logically equivalent to P and P implies Q. So P and P implies Q. And so P and P implies Q is logically equivalent to P and, now P implies Q is the same as not P or Q. You have to remember that P implies Q is the same as not P or Q. Now we can use distributive law to expand this, and the distributive law tells us that this becomes P and not P, or P and not P, or P and Q. That's distributive law. Now P and not P is always false. Remember we said P and not P is false. If P is I am inside and not P is I am outside, I cannot be inside and outside at the same time. So this is false for P and Q. Now false for P and Q just leaves P and Q. Why is that so? Because if P and Q right here together is true, then false or true is true. But if P and Q together is false, then the result is false, which is still P and Q. And so the result of OR in this case depends on P and Q. And so this is logically equivalent to our right hand side. And so this gets rid of question 2 using laws of algebra of proportion. Easy, soft. Nice. So that's question 2. Alright, so let's go to question 3. So question 3 says to verify with algebra of proposition that the negation of P and Q or P and Q is a tautology, and verify with a truth table that negation of P and the negation of P or Q is a contradiction, then show using algebra of proportion that that thing there is a tautology. So let's start with the first one, and it says using algebra of proportion. So using algebra of proportion, we need to show that it is a tautology. So the first one is our left-hand side. So what we're trying to do is showing that the result of this is always going to be true. So we have the negation of P and Q or P and Q. And so this is now logically equivalent to the negation of P or the negation of Q. This works out to be the negation of P, then the negation of and is or, negation of and is or, so we get the negation of and is or, and then we have or the negation of Q or P and Q. So that's it. So we have the negation of P or the negation of Q, and we have P and Q. Now clearly this is a tautology, but how we're going to demonstrate this now mathematically. Alright, so one way I like to look at it is, so this is what we have in reality. If I were to let P and Q be represented by a third variable R, so let R stand for P and Q, right? If R stands for P and Q, then not R is going to be the negation of P, not R is going to be not R. So not R is going to be the negation of P and Q. We agree with that, right? Yes. Not R is the negation of P and Q. Put this in a bracket. And so what this statement is actually is the statement that we actually have then is that our left-hand side is really logically equivalent to the negation of or the negation of R or R. Now, if R is I am inside and not R is, if not R is I am outside, so I am outside or I am inside, that is always true, right? We discover that this has to be true, and so hence this is always true, and so it is proven to be true all the time. All right, so we just looked at that law from the table of laws of algebra of proportion. So that's the first one. The second one says verify with a truth table now that not P and the negation of not P or Q is a contradiction. So let's verify this one with a truth table. Let's try to fit it down here. I'm going to try and fit it down here, instead of going to a new sheet, since the question is right here. So we have P, we're going to need P, then we're going to need not P, then we're going to need a P, not P, then we're going to need not P, we're going to need, oh, we left out Q, my apologies, Q is left out. Q is left out, so we're going to need not Q, then we're going to need, we need P, we need Q, we need not Q, and not P, so let's write not P, not Q, then I'm going to need not P or not Q, then I'm going to need the negation of not P or not Q. Then I'm going to need finally the negation of P and the negation of not P and not Q. So a lot of work to do right here. So let's complete this one. Very easy question. Alright, so let's go now. So P is going to be true, true, false, false. And so Q is going to be true, false, true, false. And so not P is going to be false, false, true, true. And so not Q is going to be false, true, false, true. And so not P or not Q, we're going to look at not P or not Q. False and false is false. False and false is false. False and true is false. Then we're going to have true or false is false. And then true or true is true. Then we need the negation of this right here, which is then going to be true, 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 false. Then we need the negation of P and the negation of the negation of P and the negation of Q. So we need the negation of P and this table right here. So false and true is false. False and true is false. Then false and true is again false. And then the third one is true. So not P right here is true. This table right here is true. Right, something is on. So let's look at this now again. P, not P is going to be false, false, true, true. Not Q is going to be false, true, false, true. So not P. Oh, here's the mistake. Not P or not Q. Not P, false or false is false. False or true is true. False or true is true. Then true or false is true. Right here should be true. This one right here should be true. That right here should be true. And then the negation of true. Negation of true is false. And then we have true or the last one. Then we have true or true. True negation is false. Yes, this is fine. So now we have false and true is also false. And then the final one we're going to have is true and false is also false. And so because the entire column right here, everything is false, then clearly it is a contradiction. So very easy question, very easy. So I want you to try that third and final one for yourself. Show the algebra proposition, algebra proportion, that is a tautology. So try, take 5 minutes and do it. So pause the video, take 5 minutes to do it. Alright, now let us do it together now. So show that P implies Q or Q implies P is a tautology. So to show that P implies Q or Q implies P is a tautology. P implies Q or Q implies P. So I want to show that this is a tautology. So first we're going to start with our truth table. P, Q, P implies Q. We're going to need Q implies P. Then we're going to need both P implies Q and Q implies P. P implies Q or Q implies P. That's what we need. So let's look at this now. We have P, we have Q, we have P implies Q, we have Q implies P, and P implies Q or Q implies P. Alright, so P is true, true, false, false. Then Q is going to be true, false, true, false. True, false, true, false. And so P implies Q is going to be P implies Q. The only time it is false is when the antecedent is true and the consequent is false. So whenever P is Q is true and Q is false, then in that case P implies Q is false. Everywhere else is true. Then Q implies P now. Q implies P. Whenever Q is true and P is false, that's the only time it is false. So when Q is true and P is false, that's the only time it is false. So then everywhere else is true. And then for both of them now, right here, we have true or true is true, false or true is true, true or false is true, then true or true is true. And so the entire column right here shows that the result is true. And so hence, this is a tautology. This is always going to be true. But it did not want us to do it using, truth table. It wanted us to do it using laws of algebra proportion. So let's use algebra proportion to do this question. So to do this question, we will have P implies Q using algebra proportion, or Q implies P. So now remember, P implies Q is logically equivalent to not P or Q. P implies Q is logically equivalent to not P or Q, or now Q implies P is going to be equivalent to not Q or P. Now how do I know that? Now if P implies Q is the same as not P or Q, imagine you replace now the P with Q. So the result become not Q, or and replace the Q now with P. So you get or P. So that's what we have now. We have that this becomes not P or Q, or not Q or P. Now think of the or as plus. Everything has a plus sign. Imagine you have 1 plus 2 plus 3 plus 4 plus 5. You can group it up any way you want now, right? You can add it any way you want. So I can just get rid of these brackets by writing it as not P or Q or not Q or P. Now I'm then going to group the not Q and the Q right here. Because what happens is that Q or not Q, that is always true. Q is either, if Q is I am inside and not Q is I am outside, then I am either inside or outside. That is always true. So this works out to be not P or true, or P. Now look at this now. Now not P or true, not P or true. Anything or true is true. So this works out to be true or P. And then true or P works out to just be true. True or P works out to be true. And so indeed using algebra proportion, P implies Q or Q implies P is true. Easy question, soft. Alright, let's look at one final question.